So, my name is Ted Blackman. I'm here to talk to you about Ford, which is Urbit's build system. So Urbit is a operating system written as a pure function. Ford is one of Urbit's kernel modules, so it's part of the operating system, and it is a build system. So go through, like, what is a build system? It's actually kind of hard to find a good definition of a build system. This is the one from Wikipedia, more or less. A software tool designed to automate the process of program compilation. It's kind of boring. I think a slightly better definition is this one, which is that a build system provides a language where you can express a transformation from a set of source resources to a target. And those source resources are usually files, and the target is usually an executable program. Build systems usually do something like this, right, where you have hello.h is a file, hello.c is a file, hello.io.c is a file. There's some relationship among all those. We compile those two to get object files, and then we link those together to make an executable. And so there's this directed acyclic graph going from left to right, and then hello there is the final executable. And we can do this sort of thing in Ford, but Ford is not. It's not quite as simple or single purpose as your average build system. And in fact, there's a bunch of stuff that we can do with Ford that you can't do with, say, make, which is what your grandmother used. So here's some things that we use Ford for that people don't necessarily use build systems for in other systems. One is executing shell expressions. So if you type an expression into the REPL, that gets sent to Ford to be executed. Ford is used by Urbit's version control system. So Urbit's file system is called Clay, and among other things, it implements version control on all the files. But in order to actually perform the diffing and merging and patching operations, it delegates those to Ford. And similarly, file type validation is performed by Ford. So Clay is a statically typed file system, but actually the performance of validation of those types is done by Ford, not by Clay. The last two are kind of getting into some of the more interesting ones. So we use Ford to generate static websites. And I say static, but I'll explain later that they're also reactive. But you can have some files, like markdown files or other text files, in your file system. And if you put them in the right place, then Urbit's web server, which is called Air, will make a request to Ford, which will then make a request to Ford that's asking it to perform a build of those files. And the build that it performs will run those files through a whole pipeline until an HTTP response comes out containing HTML. And finally, we have a unit test runner, which is actually pretty new. It was just added a couple months ago. And it will recursively spider through the file system, starting at the path that you give it, looking for files, Hoon source files that contain tests, and then it will go and run all those tests. And it will run them each in a virtualization context so that it can capture errors. But the finding and running of those tests is done as a Ford build. So these are the things we're using Ford for at the moment. And the reason we can do these things is that Ford is actually a very general system. So it can do a lot more than just that. And in fact, it's a generic system for running staged asynchronous computations. So basically any pipeline of computations that you want to run that start from some resources, whether those are just like literal data structures or parts of the Urbit namespace, which is generally the file system. So like starting from files or folders and starting from like literal inputs if you want to run some computation that says, okay, we'll do transformation A to those inputs, and then wait asynchronously to hear back from remote server B, and then join those two things and run a build on that, and then run some other build. You can ask Ford to do that, giving it just like a declarative specification of the build, and it will figure out the scheduling of that whole pipeline. And it'll run it and give you back the result. So actually, we want to use, probably long-term, Ford is going to become the general system scheduler for Urbit. So it's almost certainly going to eat some of the functionality of some of the other kernel modules, like the application sandbox, and be used for even more things than it is right now. So here's some properties of Ford that are unusual for build systems. And you can probably find build systems that are maybe 2 or 3 of these. I'm not sure if there are any others that actually satisfy all 4. If you know of any, then let me know. One of Ford's biggest advantages is that it's referentially transparent. So like, referential transparency is, of course, like a cornerstone of functional programming in general. And one of the things that we try to do at Urbit is provide referential transparency at many levels of the stack. So the kind of lowest level is that Nock itself, the virtual machine, is a pure function. Pure functions are referentially transparent, more or less. It's a very similar concept. And then our file system is referentially transparent. Ford is referentially transparent. And we also have this concept of the global immutable namespace. And that is also referentially transparent. So that's just basically this kind of sort of generalized file system that lives across all of the Urbit nodes, like all of the Urbit servers. So you can request some file that's on your server or on somebody else's server. You may not have permissions to it, but the semantics of that are that it needs to be referentially transparent. So Ford is referentially transparent in the sense that if you ask it to perform a build, you send it a data structure representing that build, and no matter when you send Ford that data structure, no matter how many times you send it, when the build completes and Ford sends you back the result, it will always be the exact same result. So the reference to the product of the build is transparent in the sense that you can replace it with the actual product of the build and have the same semantics. So hence referential transparency. There are a couple of other referentially transparent build systems, and people love them for that reason. Nix is the one that people are talking about here, mostly. It's a really nice feature. And in fact, a lot of the problems that people have with build systems come from the few places where build systems deviate from referential transparency. Anytime you have sort of non-determinism in your build system, it leads to really bad things. Okay, so the second one is reactive. And this is pretty unusual, actually. Like a lot of build systems will do incremental rebuilds, but most of them don't provide a facility where you can say, run this build, and then also I want to subscribe to this build, so that if any of the source inputs change, then rerun the build and stream down the new responses to me in like a functional reactive programming paradigm. All right, so Ford does this. All right, you ask Ford to run this pipeline that starts from some source files, and then when the version number of the source files increments, somebody overwrites them with new files. And of course, because Clay is referentially transparent, that means that you can't just overwrite the contents of a file path, but you can increment the version number in the file path and write that. And so when that happens, Ford maintains a subscription. Like when you ask Ford to first perform this build, Ford starts a subscription to Clay on whatever files are dependencies for that build. And then whenever any of those files get overwritten with the new version, Ford hears about that from Clay and then starts rebuilding the build and sort of rebuilds the pieces of it that need to be rebuilt and then sends you down a new version. And this continues every time one of the files changes. You guys following that? All right. So the next one is type safe. I think this is actually very unusual for a build system. I think the vast majority of build systems are sort of dynamically or softly typed. But with Ford, everything is typed using the file system's typing system. So just as Clay is statically typed, so is Ford. Statically typed might be a little too much because the builds are actually very dynamic, so you don't necessarily what type it's going to come out as when it's done, but you know that whatever type it comes out as, it'll be verified to be a valid value of that type. And then finally, it's asynchronous. So if you request some, if a build depends on some resource that's on someone else's server, Ford will yield execution to other things on your server until it hears back from that other server with the result. So here's an example of a build that Ford could run. The final structure of the build looks like this. So it's a DAG. The final result is going to be the result of running this build. And then these are leaf builds here. So like these are, say, files. So in order to run this build, we start with the top. Well, all we're given is that top, the request, which is just the top build. When we try to run that, we discover that it has 2 dependencies. But when we try to run the left one, we discover that it has another dependency. So all these things are blocked. They're not done. They're not done until they turn green. And then that dependency in turn has 2 more dependencies. But it turns out those are leaves. Those are files. So we can actually run those builds. We can request the files, get the contents. So we get the contents of this one. Then when the contents of this one show up, then we say, OK, well, this build was blocked on these 2. So now we can go back and run this one. And that goes back up here, et cetera. And then there's actually another interesting point where it's like, OK, once we finish this, then we're going to try to run this build. But when we try to run this build, we discover that it depends on this leaf build, but that it also depends on this other build. But because of the way Ford's caching system works and dependency tracking system, this diamond here gets deduplicated. Right? So these 2 both depend on that. Right? But we don't have to rerun this one. We already know that we've got it. So then we go and build this leaf node, and then we can build that one. And then once we've finished this one, then we send you the response. Make sense? So this is a rather bold claim, but one thing that we can do with Ford is avoid dependency hell. So how many of you have ever been in dependency hell?
A couple times.
Yeah, a little bit. A little bit. It's really fun, right? Yeah. A lot of the reason for dependency hell is that you might have, say, 2 different libraries that both depend on some other library. Right? 2 things that both depend on, say, OpenSSL. But then one of them depends on OpenSSL version 2.1, and the other one depends on OpenSSL version 2.2. And how do you resolve that? And in a lot of cases, you're just screwed. Like, there's just nothing you can do. Often there's some kind of workaround, but this is generally a really big problem. But because of the referential transparency underneath all of this stuff, we can actually resolve these things. So here's some example of some Hoon code that uses Ford. So this fazlus here means import a library. So we're importing a library named libname. This is from our server. And let's say it's called ourlib. We're going to name it ourlib. Right? We're going to import it as ourlib. And then let's say we also want to import a library that's the same library, libname, but from a remote server. Right? So in this case, we're importing it from a server called Zod. But what happens is these just come into the namespace of your program as 2 entirely separate things. And so if there's some symbol foo that you want to use from our version of the library, you can do it like this. And then the projector can die. Hey, all right. So if there's some symbol foo, you can pull that out of our lib. You can also pull out foo from zodlib. This here just makes a pair of those 2 things. And those are totally separate things, no conflicts. And the cool part of this is that this actually goes down all the way to the standard library. So if in order to build libname here, let's say you needed an older version of Hoon, and you needed an older version of our standard library, this thing would be built against those older versions. So you can even have kind of like different versions of the kernel living separately. And the reason this works because of both referential transparency and because they're actually just represented as knock trees, and knock trees don't change. So Ford does some pretty cool things, but one thing that it doesn't do at the moment is complete in a reasonable amount of time. And so the reason for this is that it actually just doesn't do incremental rebuilding very well. So current Ford, so incremental rebuilding happens when one of the leaves of some live build changes, right? So let's say this leaf, somebody overwrites this file with a new version. So then what happens is Ford will receive that notification from the file system, rebuild this thing, and then because this is a different value, it'll go and have to try to rebuild this one. Now, what this should do, and so I'm rewriting Ford, this guy Elliot Glacier and I are rewriting Ford from scratch. And so the new version does this right, where it tries to run this build, but it knows that this build here, which this one here depends on, it knows that this one hasn't changed because we heard back from the file system that this one changed, but that implicitly means that when this one changed, that means that these two did not change. So because we know that these two did not change, that means that we know that this one didn't change. So we can promote the cached versions of those builds and add a new cache where a new key pair in the cache where the key is these files, but with the version number incremented. And so then when we go to rebuild this thing, we already have the new version of this build in the cache. And so we don't have to rebuild this. We just rebuild this one. And the other smart thing that new Ford does is that when we rebuild this one, we compare the new value against the old value. And so then if it turns out that it was the same value, then we don't go and rebuild the top one, right? And we don't go and rebuild. So in general, like often what will happen is there's some sort of, this actually happens all the time, because often what there'll be is a build that just takes a small piece of something, right? So like if you have a fora post, right, or a blog post or something, and there's some sidebar that's listing all the titles, right? But then let's say you overwrite the contents of some fora of that post, you don't change the title, like this thing changes, but this one doesn't, right? If this build is grab the title from this build, right, and you just change the contents here, then this thing doesn't change, right? And so then because this thing doesn't change, that means that all the generally like a few hundred builds that all depend on this sidebar, right? Because every page depends on the sidebar. Right? But we actually, by knowing that we don't have to rebuild that sidebar, we avoid a ton of extra work. So new Ford does this. And so this is like a real incremental rebuilding system. And that's it. So thank you. You guys have any questions or want to see some code? Yeah.
When can we expect new Ford?
That's a good question. My boss asked me the same thing. I'd say 2 to 3 months. So the current status of new Ford, which is called Ford Turbo, by the way, Ford-Turbo. It's a Git branch. So it's a branch on GitHub. There's also, and I can send out some links. There's also, we wrote up a proposal for Ford, and it's on Urbit's fora. So if you want to see like the full design of how we do this, it's kind of a long proposal, but it's up there. Yeah, so the current status is that we have a full implementation of Ford in the sense that we built all the functionality we think we'll need. And unusually for Urbit, we wrote a full suite of unit tests. So it's thoroughly tested. Unit tests. They test the whole module. So call that a unit test or call it a black box test. The line is a little fuzzy in this case. But so we have this complete tested system, and just last week we we built it as a library, standalone. But just last week, we took it into the kernel and added it as a new kernel module alongside existing Ford. So this is the bootstrapping process of like how do you actually get a kernel module to be real, right? And so at first we just loaded it, but nothing was trying to make any requests of it. So it would just sit there and it would look pretty. And then then we took the shell, which is called Dojo, the REPL, and we converted that to use new Ford and send requests to it, and we got that working. So it's at least being used a little bit in our thing. So then we have to convert. We still have to convert Clay, the file system, Air, the web server, and Gall, the application sandbox. All use Ford, and some of those have pretty detailed interactions. So that'll take a while just to get the integration right. And then there's also, we discovered that the caching semantics of new Ford need some help. So actually, Gavin was helping me with this yesterday. But so we basically need to add a cache. Right now, what we have in new Ford is not so much a cache. It just holds on to the dependencies, and it holds on to the most recent build and all the sub builds for each live build. So each build that you're subscribed to with Ford Ford will hold on to the latest versions of all of those so that it can use those for promotions. If some dependency changes, it can use the old versions to hopefully promote those to the new time. But it doesn't really have a cache per se, right? So if you just ask it to do a one-off build, so like build this thing but don't subscribe to it, then Ford would just build it and then throw the whole thing away. And it turns out that this really isn't great because a lot of the patterns of use for Ford involve, say, like the shell, right? You type in some expression, and then maybe you type in the same expression again, or maybe you type in some expression that's almost the same, that where like 7 of 10 of the sub builds are the same. Right? So in that case, you actually want that cached so that you can reuse those 7 of 10 sub builds, right? So we're adding a cache, probably like a pretty simple LRU cache. So 2 to 3 months, that's the guess.
So I have a different question. If you go back a couple of slides here to your graphs, I think.
Yeah.
So from what you were saying, it sounded like, I just want to confirm this.
Yeah.
When one of your files updates and you're triggering, an update of the versioning, right? So
Yeah.
you put a new version tag on the build result, right? So like the final node there, the top node, the root node,
Yeah.
gets a new version, right?
Sort of.
Or does it, but I guess the question is, does it get a new version always, or does it only get a new version if like that dependency propagates the change up to that layer?
It only gets it if the dependency propagates a change up to that layer. So, so let's say that instead of this one changing, let's say this one didn't change. Let's say this leaf changed, right? And then let's say this leaf changed, and this build changed, but this build didn't change and this build didn't change, right? So in that case, well, the actual flow of execution here is that we rebuild this, right? Both of these changed. And we rebuild, wait, or did I say? No, this one didn't change? I don't remember. It did? Okay, so this one changed and then this one didn't. So when we rerun this one and it didn't change, then we don't even try to rerun the top one, right? And so the dependencies that we track end up for a given live build, different sub builds might be at different times, like at different old times. So you could, like, let's say if this file kept changing over and over again, but then like none of the other builds changed as a result, then like you'd have kind of like all the dependencies, like all the sub builds at this really old timestamp, except for that one that's gone up here. And that's actually done as an optimization because if you think about it, man, what is wrong with this projector? So if you think about it, let's say there are 300 builds. Let's say this is a sidebar. There are 300 builds that depend on it, and this is actually a a realistic use case, like this happened. If you so not, actually, there's another optimization here, which is that not only do we hold on to the latest version, but if there's some if there's some client build, like a parent, that depends on that was built using an older version of that sub build, but then when we rebuilt the new version, that turns out that it didn't change. What we do is we store the fact that those two are the same, and then so the linkage goes in this like L,
Right,
like
so
that.
keep just the new version.
And that means, because otherwise, if we move the linkage from like parent build to sub build to the new sub build, then we would have to do that for every parent. And in general, so in that case, there'd be several hundred parents. 300 is not like the end of the world necessarily, but we want to be able to. We want this thing to scale, right? Like we want it to be at least usable as a spreadsheet backend, right? So like, ideally, you should be able to have 10,000 rows, or 10,000 rows in some column, and then have the column next to it have each row be a function of the previous row, and if you only change one value, that should update quickly, right? And so if we didn't have that optimization there, then you'd actually have to move 10,000 references every time something reran and got the same value. So this adds a little bit of extra work in the like cleanup stage, where you have to, like when we're done with that, we kind of have to follow that L to figure out which builds need to be deleted at which times. But that's not too bad. Does that answer your question?
I think so.
Okay. Yeah.
So for future caching, are you going to integrate that into the file system so you can have like a Zod binary cache?
Maybe.
So you have this existing method of doing a distributed binary store that you see in a lot of really advanced distributed build systems. And it seems like you already have the baseline for most of those things.
Yeah, there are a couple of different ways that we could implement something like that. One would be that you would have, if you depended on some resource that's on some other ship, some other server, right? So if you depend on a resource on Zod, you're like, I'm on my planet, and I depend on some resource, some file on Zod. Right now, if you depend on the file, then it'll actually be pretty slow, and it'll fetch that file and then try to build it. And when it tries to build it, if that file depends on other files on Zod, it'll go make a bunch more network requests, right? And fetch those files and build those, right? And so that becomes untenable really quickly. One thing we could do is we could sync a desk. So Urbit has desks, which are basically like Git branches, and you can sync them from server to server. So if I know what branch I'm trying to build something on, what desk I'm trying to build something on off Zod, I could actually have that just like sync that whole desk, which is its own sort of, that becomes one big network thing. And it gets sent down as diffs, so in general, unless it's like a really old and very different, it probably won't be that different from what we've got here. So that's not too bad. But it's a little bit weird to kind of like, it's like the abstraction there feels a little wrong, I think. So there's another way that we could do this where, if you want if you want some build to actually be available to other servers, then you make it available through, probably through Gall, which is our application sandbox, or maybe through Air, which is our HTTP server. And it's an HTTP server, but there's also like a kind of like a tunnel for if it's for Urbit to Urbit communication. But it's basically like a way to sort of announce or like to listen at a well-defined endpoint. So we could have so maybe Zod says, I want to make this library available. I actually want to make the built binary of this library available, and it'll make it available at some Air endpoint, or maybe like through some Gall app. And so then we do plan on adding functionality to Ford where it can actually depend on, it can subscribe to like a pub/sub feed from an application. Because Gall applications work as pub/sub, where you can subscribe, and every time the data changes, it'll send you down, stream down a new message to you. So sort of next on the docket, once Ford is sort of basically working, we're going to have it be able to subscribe to Gall. And so then we could also have it subscribe to a remote Gall, such as from Zod, right, from this remote server, and then get the binary that way. And the binary is going to be a just a bunch of knock that's just serialized. Right? I don't know. We don't usually load programs that way, though. Like the actual serialized knock of a program, I'm not sure how that compares in size to the Hoon that generated it. Like the Hoon that generated it is probably pretty small, but the compilation time, I don't know.
Yeah, I mean, even like, not that the current state of the art is great or anything, but in the rest of the world,
Yeah.
it's not uncommon to have, the source code program be far, far smaller than the binary.
Yeah. Well, if we do good caching, then... No, that's not a real answer. Here's what I was going to say, but it doesn't work. I was going to say that if you're loading some application off some other server, but that it's actually broken up into many source files that depend on each other, good chance we'd have a lot of those files on our server already. I don't think that's actually true. So, yeah, I guess we just... I don't know exactly how we'll do like binary distribution of packages. The other part that's a little tough about that is that normally when we're running any of these things, we actually have the type of the program available to us. The programs are statically typed. And so normally when we're dealing with programs, like when we compile them ourselves, you have to compile a program against a subject type. And then that produces a, in a knock subject and formula kind of way. So basically, you have to, it's essentially like a linking process. It's like whenever you're running the compiler, you're actually kind of like linking it against usually the standard library, maybe some other stuff too. But when we do that, that's done in a type-safe manner, and so we run type inference over the code, and that tells, like, starting from the subject type, and then whatever code that we're compiling that's supposed to run against that subject, we forward type inference across that, get to the product type that we expect. And so that's actually used for like making sure that we can run each step of a build and verify the types along the way. So if we're just pulling in straight knock with no types, then I guess we could validate it just the way we validate like untrusted network data. So, and we can use the type system for that, and we have to use the type system a little bit differently. That's probably the way to do that. So okay, so my answer actually wasn't terrible.
Wait, but does that mean that the Hoon level types are latent in the knock that's outputted?
They're not. They get stripped out during compilation, but the compiler will generally produce a pair of type and knock.
Okay.
Yeah.
Where knock is.
Knock is like the program that you're going to run. That's the executable. But then. What?
That's part of the demo I had to skip over.
Oh, was it?
Yeah.
No, that's too
Awesome.
bad.
Man, it was
You can do it
amazing.
now. It's really fun.
Yeah. You wanna?
Oh no, that's
All right.
Get it on video.
But yeah, so normally the compiler produces a pair. So it's got the type information, which can be used for reflection and validation, that sort of thing. And then there's the executable, and the executable has no types in it. Knock is untyped. Are you familiar? Are you guys familiar with Hoon and Knock or Urbit at all?
Yeah, roughly.
Okay, cool. So I'll give a little bit of background here, just as a refresher. Knock takes a subject and a formula, and the subject is basically the argument, and the formula is basically the function, and it runs the formula against the subject. All of these things are binary trees. So when you run a formula against the subject, the formula is a binary tree, the subject is a binary tree, and the result of evaluating it is also a binary tree. So Urbit itself is a sequence of those evaluations, right? So every time a new event comes in, it runs knock on that event, produces a new tree, and that tree contains all of the programs and all of the data that are in your operating system. So it produces like a new version of the operating system every time you run an event. Now normally it's the same, basically the same operating system, but it can also hot reload itself for this reason. And so that's at the knock level. So knock is the VM. It's like a little micro Lisp, right? Just binary trees. Hoon is the language, the programming language that you actually use that compiles down to knock. So when I'm talking about compiling, I'm talking about compiling Hoon down to knock, which then gets interpreted on an event basis. So all the types in Urbit live inside of Hoon, basically, but they're all represented as knock trees. And Hoon compiles itself. So there's like bootstrapping happening here at like 3 or 4 different levels. And so like in Hoon, often what you'll end up doing is you'll call the Hoon compiler as a library on some Hoon source, and then that'll produce this pair of type and knock, and the type itself is a binary tree. But then you can use that to, even though it's a static type system, there are facilities for working with types and transforming them and checking them against each other and validating pieces of data against those types at runtime as well. So, but yeah, so this is one of the tough things about trying to load binary, like just a compiled binary off of some other server, is that you wouldn't usually have the type information that comes with it. And so what you probably have to do is like do that under some sort of constraint, such that like once you've compiled it, you actually once you've compiled it and run it, then you should have some validator that you use on the result to make sure that it's all safe. Does that make sense? All right, cool. You guys have any other questions?
Just a niggling curiosity question.
Yeah.
What's the type of the version control number of a file?
It's called a case. And it's either a numeric like just a unsigned integer number, which is the version number, or it's a date, which is represented using Urbit's date format. It's like a 128-bit integer with some pretty printing. And then, or it's a label. So a label is kind of like a git tag. We'll see. We've had some discussions about maybe removing the numeric version numbers. Internally, Ford just uses time. And the reason Ford uses time is because, like the date. The reason Ford uses that is that Ford needs to actually be reactive to many different streams of data. Right now, it's only reactive to the file system. The next step is to get it to be reactive to subscription data from applications. But subscription data from applications doesn't have a numeric version number. Only the file system has a numeric version number. Whereas like requesting paths by time is something that can be done all across the operating system, all across the global immutable namespace, right? Which isn't just the file system. It's actually like each kernel module can expose data into that global namespace, and so can applications. The file system as a kernel module exposes the file system itself into that namespace. But we've talked about doing other things like with that. So for example, we could have, like we're building an Ethereum connector in one of the kernel modules, so it can read from the Ethereum blockchain. And so one thing we could do is actually make that data, have it expose that data into the Urbit namespace. It's all immutable anyway, so it's referentially transparent. So it's kosher, right? Like
Completed blocks, though.
what?
Always looking at only the completed blocks.
Yeah, we've actually had some discussion about how to make that referentially transparent. So you could have like kind of 2 different dates. There's like the date that the date when Urbit thought about it, and then the date when I don't know the details there.
Do you want like a validating checksum as a way to provide like an additional, like, why isn't like a validating checksum of the output not with the kind of discriminate you would want on the version?
I mean, I think well, what would you use it for?
If you're going to serialize the knock to another node on the network, and they can at least check the bit and get man in the middle attack or something.
Oh, well, so that's handled at the Urbit networking protocol level.
Okay.
So Urbit uses its own networking protocol. It goes over UDP, but every packet, so it implements something that's similar to TCP, but it implements it over UDP, and there's a number of big differences. One of the big differences is that every packet is signed and encrypted.
Okay.
So your Urbit has one public-private key pair that it uses for networking. So you'll sign every message with your private key. Everybody knows your public key. They can use that to verify, and then you also encrypt it using their you encrypt it so that only they can decrypt it. Using their public key. So then and then that's all end to end. It's peer to peer. So it doesn't really go through anybody else. But because it's encrypted, nobody else has access to those keys. So so we don't have to worry about that exactly. Well, one thing we do have to worry about in general is that Urbit is not a blockchain, and that means that anybody can always lie. All right, and lying in this case means that it means violating referential transparency, where I can ask you for some file once. Right, I can ask you for some file, and you're like, sure, here's the file, and then Justin asks you for the same file, and you give him something totally different. Right, so that's violating referential transparency. We can't directly prevent that with our networking protocol because it's not a Byzantine consensus, right? Which is part of why we're going to interoperate with blockchains. So if there's data where we really need that sort of thing, then one thing we could do is use the blockchain as a notary. Right, so sign the hash of the result of that path and the path, put that on the blockchain. That way anybody can see, okay, well that's what he said, right? He said it was going to be this hash. So if you ever find something that was signed by you for that path with a different hash, then you can publicize that, be like, look, he lied. And that'll have a very big reputation cost for you. And because the identities are permanent cryptographic identities, that would actually damage your ability to have a decent reputation on the network.
You'll never work this down again.
Right. not in this cosmos. You guys have any other just general Urbit questions? I can keep talking about this forever. Or did I dump too much into your brains already? I have a tendency to do that.
So do you do most of the UI stuff?
No, I don't do any of the UI stuff.
Okay. Who wrote the web server stuff, or the front end stack? Because you guys have this.
Anton wrote a lot of that, but we've since moved to a different one that was written by this guy Isaac, so that's the web rendering stuff. But then the front end itself is being completely rewritten, and so are the chat and fora apps, and that's all being. So we're working on a project that we call MVE, minimum viable exit, an exit from existing internet, right? It's not actually, you won't actually be able to completely exit, but the idea is that you'll be able to use Urbit for messaging and for text-based content, and that it'll be easy enough to use and reliable enough that you can at least use it even if it's not fully mature. But the early adopters can use it.
From a perspective, are these types of things that you're talking about writing, are they subject to change forever, or will those types of things be stabilized?
So none of the kernel modules have been Kelvin versioned yet. Are you guys familiar with Kelvin versioning?
That's what I'm
Okay. Yeah, so none of the kernel modules are currently Kelvin versioned. The standard library, Zeus, is, but it has a pretty high. I think it has a really high Kelvin version. It's in the thousands, I
You
think.
have 3 numbers on your shirt, so
Yeah, right. That's what I was just thinking, actually. Okay, so 5 Kelvin is Nock, 144 Kelvin is Hoon, and then 309 Kelvin is Zeus, the standard library. I think Arvo has a Kelvin version, but I mean, I could be wrong. If so, it's really high. Like we're nowhere near being done with Arvo.
Okay, so
We're definitely nowhere near being done with the veins.
like, there's no plan to have like a frozen UI layer or anywhere in the near future.
Not anytime in the near future. I mean, we don't even have a GUI vein. The closest thing we have is Air, the web server, which is in effect our GUI vein. Right? Like, there is a way to use a graphical user interface with Urbit, and it's over the web. And in fact, that's going to be the primary way that people use Urbit. And it kind of already is. But we're kind of delegating the G in the GUI to browsers. So I think long term, I suspect what we'll end up with is something like an actual GUI vein, right? Where there will be some type data structure that represents something like a DOM. And we'll just, like Arvo itself will just rely on var, the interpreter, to perform the effects of changing the screen based on that type data structure. That make sense?
So that static DOM, would that be a replacement for your browser?
Maybe, or maybe we'll like use some, horrible Electron app or something to, render it.
See, my claims are all true. It's true of iPhones.
Yeah, we're working on a mobile app too.
See, I told you.
Maximum viable energy consumption.
Mm-hmm.
This is how it's so easy. Everyone can use it. And, have nice clean UIs.
I mean, I'm really looking forward to.
Plus going to have template metaprogramming.
Oh, it does.
It does have polymorphic types. Similar idea. But we are working on we're working on a mobile app. I'm really excited for the mobile app because I like being on Urbit Talk, but you can't really use it from your phone, not very well. And just a website doesn't really cut it. You can't get notifications, Yeah, I think that we kind of have to have that to complete the user interface story there.
Oh, yeah, get the core functionality in place, the messaging, identities, website, and stuff like that.
Yeah.
About half of that is okay.
Yeah. And we're working on HTTPS right now also. So.
Is that something that should actually go on the Urbit layer? As
It's
opposed
no
to,
the SSL.
Nginx in front of
The
it?
SSL termination is done in C. So we're not using Nginx, we're using H2O, but it's very similar. And it's embedded into var. We didn't want to have to run yet another process,
But this is at
right? Because we want this to.
implementation layer, not the.
It's not inside of Arvo. It's not inside of Nock. It's out. The SSL termination itself.
And it will
the
stay
pr- the-
that way,
Yeah. No, we use
The event.
we use libh2o and OpenSSL for that. You don't want to mess that up.
Yeah.
And I mean, I think OpenSSL has messed it up enough, really.
So even if you did implement them, you'll be stuck with it for.
Right. Yeah. But I guess there is a bunch of it that we're implementing inside of Urbit though, and that's the flow for obtaining a certificate using Let's Encrypt. So that's we'll have what?
Just similar to Certbot.
Yeah.
I've kind of been out of date for a while, so it sounds like you can compile C programs into Urbit.
No. Forward is for compiling Hoon programs
Well, you're
and linking them.
libh2o and OpenSSL.
Oh, so those are part of the runtime for Urbit. So we call that var. So that's the program that runs on Unix, that runs Urbit. And I like to think of it as sort of like a CPU and a motherboard. Right? Basically the CPU kind of just performs calculations, and then the motherboard has all these hardware devices for receiving messages from other devices, and then having these various kind of actuation functionality, right, where it can actually make bits flow over a wire, right? So the part of Urbit that performs effects is var, which is like the motherboard, and then Arvo is just the Urbit operating system, and that's a pure function. Yeah.
So it'd be like the terminal, basically. That instead of that, it's just SSS.
Yeah. Yeah. Well, thank you.